In this video, I want to go quickly over common mathematical notations, so symbols and expressions that mathematicians use and that you should know about so you are not lost in your lectures. Let's start with sets. So for example, the set 2, 3, 4 is the set with the elements just 2, 3, and 4. And those are unordered sets. So this is the same, is equal to the set with the elements 4, 3, 2. If you instead want some ordered list, then typically round parentheses means that that is an ordered list, and this is the first element of the list, second and third element of the list. So this would not be equal to 3, 2, 1, where the order matters. If we want to denote that an element like 2 belongs to this set, we usually give sets names, so let's say that's set S, then we write 2 belongs to the set S. So this symbol right here means in or belongs to. You can also say that something does not belong to the set, so we would also say that the number 1 is not in the set S, so that means that it does not belong to that set. If we want to denote the size, usually lines like that, so if I have the set 1, 2, 3, and I write lines, that usually means the same as the hashtag set. That means the size of the set or the cardinality of the set. In this case, is just there are 3 elements. We also have notation for containment. So we say that the set 2, 3 is contained in the set 2, 3, 4. And we also write that symbol is contained or equal, or we can just write containment without the equal to say that 2, 3 is contained in 2, 3, 4. But if I want to make sure that I'm emphasizing that it's contained but not equal, then we have another symbol for that, which is that it's contained but not equal to 2, 3, and 4. Now, if it is not contained at all, then we can cross the symbol completely. So 1, 2, 3, it is not contained in the set 2, 3, 4. So we write that symbol for not contained. And then we have usually the usual union and intersection. So for example, 1, 2, 3 union with 2, 3, 4 would give me the set 1, 2, 3, 4, while the intersection of 1, 2, 3 intersect with 2, 3, 4 would just give me the elements that are in both sets, so 2 and 3. Some sets of numbers that are very common and their symbols that are common for those sets are the natural numbers. So the numbers 1, 2, 3, 4, etc. Some mathematicians start the natural numbers at 0, but I start the natural numbers at 1. Come get me. The integers are the numbers that start with -2, -1, 0, 1, 2, etc. And then we have a notation of a set for the rational numbers. We write sets with conditions sometimes. So we write these are in a conditional on a set, we write x such that, so the colon here means that I'm going to give some conditions of what this expression is. So the rational numbers are fractions of that sort, such that m and n are integers. So m and n are numbers that belong to the set of integers, and n is non-zero. Like that. Then we have the symbol for the real numbers. And we have a symbol for the complex numbers, just like that. And in set notation, this would be elements of the form a plus bi, where a and b are real numbers, and I squared is -1. That would be the set of complex numbers. Now, within the real numbers, we have subsets, which are, for example, intervals. So sometimes we write the interval a, b, and that would mean those numbers such that x are, say, real numbers, and x is strictly between a and b. Similarly, we can talk about the open intervals, or open on one side and close on the other side, meaning that the interval endpoints, a and b, is not contained in this set, but it is contained here and not here. Now, you have to be careful that this is not confused with an ordered pair, but that should come from context if they're telling you that this is an interval instead of just a pair a, b. And you can also talk about intervals of rational numbers. So if I do, for example, a comma b intersect with the rational numbers, then that means is the set of rational numbers, this time, that are between a and b. All the rational numbers that are in that interval. Okay, now let's talk about logic words or notation. First of all, I have such that. So that just means such that, and that's common, that we'll just write st for such that. Then importantly, we write this symbol for there exists. So there exists is written with that backwards e. So for example, we can say that there exists an integer n, so an n in the set of the integers, such that n squared equals 4. Yes, there is one, and in fact there are two. N being plus or minus 2 satisfies that. So this just says that there exists one, but there could be more. If you want to write that there is exactly one, then we write there is with an exclamation point, means that there exists a unique, like that. So for example, you could write that there is a unique integer such that n plus 3 is equal to 0, which is the integer equal to -3. Another symbol, a very common symbol, is this symbol, this upside down a, means for all. And for example, one could write that for all x real, so for every real number, we have the property that x squared is bigger or equal to 0. For all real numbers, x squared is non-negative. We also have implication symbols in logic. So this means, it means implies. Or if we write a implies b, I read a implies b, or it means if a, then b. And for example, I can write that if x is a real number, that implies that x squared is bigger or equal to 0. That's a sentence. We also very commonly use this double arrow to mean that it implies and it is implied, or more commonly is an if and only if, or if, and that means that it is this and these implications are both true. So when I write that A, if and only if B, this means that A implies B and B implies A. For example, n plus 3 is equal to 0 if and only if n is equal to minus 3. That means that n plus 3 equals 0 implies that n is minus 3, and if n is minus 3, that implies that n plus 3 is equal to 0. Sometimes you will also see that a professor writes TFAE. That means the following are equivalent, and if there are, for example, three mathematical statements, the following are equivalent means that every pair of those are equivalent to each other. So A if and only if B, B if and only if C, and A if and only if C. So they are all equivalent. Finally, I want to talk about function notation. So this expression, f colon A arrow B, means that f is a function that takes values from A and gives you values in B. So for every element of A, every x in A, there is a unique element of B, which we call f of x, such that x maps to f of x. This arrow with a little bar here, that arrow means maps to. So x maps to f of x. Now the set A is called the domain of the function, and the set B is called the codomain. Not everything in the codomain needs to be an image of some element, so those elements that come from A and map to something in B, those are elements in the image, and we call it the image. So the image or range of the function in set notation are those elements y in B, such that there exists an element of A, such that f of x equals y. So the image are those elements in B, such that there is some element in A that lands on y through the mapping f.